Hi everybody. Today we'll start with one more problem, that is like video model question paper problem. In that we will deal with the 1D bar element. In that question number 4a, in that a stepped composite bar is loaded as shown in the figure. Determine the nodal displacement in the bar, where P is given 200 kilonewton and cross sectional area of the first stepped bar is 400 mm square, and area is given, that is for the second step is 300 square. Young's modulus is 200 gigapascal for the first element, and for second element Young's modulus is 70 gigapascal. We'll solve this problem. And thus this is the question: a stepped composite bar is loaded as shown in the figure. So here the given data are written over here. Area, cross sectional area of this element is A1, and cross sectional area of this element is A2, and Young's modulus of this step is E1, which is nothing but 200 gigapascal, and for this stepped bar we have 70 gigapascal, and length L1 is 500 and length L2 is 300 mm. These are the given datas. Now we'll go by the stepwise solution so that it is easy to understand. The first step of the problem is to modeling and discretizing, where the given problem is modeled and discretized into number of elements. Here you can see we have two steps, step 1 and step 2. Since we have two steps, we have discretized this problem into two elements, that is element 1 and element 2. Element 1 is represented by 1 and element 2 is represented by like this. This is, you can see here. Once we do that, then we need to define the nodes, like first element is connected between node 1 and 2, and second element is connected between node 2 and 3, where node 1 gives a displacement u1, and at node 2 we will get a displacement u2, and at node 3 we will get a displacement u3. In this problem it is asked to determine the displacement, so we are concentrating only the displacements. Next, once we do this step 1, next we need to go for the second step. The second step is defining the elemental stiffness matrix for each element. That is nothing but, for 1D bar element the stiffness matrix is given by K1 is equal to A1 E1 divided by L1 1 minus 1 minus 1 1. So this is how the stiffness matrix for 1D bar element is given by, where A1 is nothing but 400 and Young's modulus is 200 into 10 raised to 3, L1 is 500. Those are the given data you can see here. So A1 is 400, E1 is 200 gigapascal. It has to convert into Newton per mm square. So then you need to multiply with 10 raised to 3, L1 is given 500. Here if you substitute this and if you solve this, you will get the answer 16 into 10 raised to 4. So there what we have done, like we have taken 10 raised to 4 outside of this matrix, then we have taken 16 minus 16 minus 16 16. If you multiply with this 1 minus 1 minus 1 1, you will get this. Once we do this, next we need to go for the second. So in the second stiffness matrix for the second element is given by A2 E2 L2, where A2 is nothing but area of the second element. Area of the second element is here, it is given 200 mm square, and Young's modulus is 70 gigapascal, which is nothing but 70 into 10 raised to 3 Newton per mm square. Next we have length is 300 mm. That's what we have substituted here. The area is 200 mm square, the Young's modulus 70 into 10 raised to 3, length is 300 mm, and the second element is connected between node 2 and 3, which we have written 2 and 3 here. Once you simplify these things, you will get 4.66 into 10 raised to 4 where we have taken 10 raised to 4 at outside, and we have multiplied this 4.66 with this 1 minus 1 minus 1 1, we have got this. So 4.66 minus 4.6 minus 4.66 4.66, this 2 and 3 represents the element 2 which is connected between 2 and 3. Next, once we form the stiffness matrix for the each element, then we need to proceed with the global stiffness matrix. That is nothing but our third step. Global stiffness matrix is nothing but addition of the two stiffness matrix which we have. Those are nothing but k is equal to k1 plus k2. K1 is nothing but our stiffness matrix for the first element, which is given here. K1 is equal to 10 raised to 4, 16 minus 16 minus 16 16. Similarly, K2 we have here 10 raised to 4, 4.66 minus 4.66 minus 4.66 4.6. These are two elements of stiffness matrix. Then we need to form the global stiffness matrix, where in this problem we have two elements, element 1 and element 2. So here two element has three nodes, node 1, node 2, node 3. Since we have three nodes, the global stiffness matrix comes in 3 by 3 matrix, that you can see 3 by 3 matrix. In this we need to add the two matrix, that we can see here. The addition is very simple. We need to see first row, first column, that is nothing but our 16. How it has came, see here. The first matrix, you can see the first row and first column we have 16, but in the second matrix we don't have any first row, we have second here, so we need to keep it as 0. So we have only first row and first column, first row first column, first row first column 16 we have. That's what we have substituted here as 16. Next, if you see first row second column, first row second column is minus 16. This you can see here in the first matrix, first row second column, that is nothing but this one, minus 16. So that you can see here, first row second matrix you can see here. Next, first row and third column we have 0, because we don't have here, we have first row but we don't have any third column, since it is 0. Once you have written this, next you need to copy these two things here, because stiffness matrix is a symmetric matrix. Once you copy these two here, you can see the same thing which I have written here, 16 minus 16 0 0. Next we need to go for the second row second column, that is nothing but 16 plus 4.66. How it has came, we'll see now. Again we need to go for K1 matrix here, second row second column we have 16 here. Similarly, if you go for the second K2 matrix, we have second row second column we have 4.66. if we add these two things, we will get this one, that is nothing but 20.66. 16 plus 4.66 is nothing but 20.66. Next, if you see second, for this what we need, we need to determine this second row third column, this is nothing but minus 4.6. How it has been came, we will see. If you go for the first matrix, we have second row but we don't have third column, so you keep it as 0, no problem. Here in this you can see the second row we have, third column we have, so it is nothing but minus 4.66, that we have substituted here. Once you have substituted this, next you need to copy this here, since it is a symmetric matrix. Otherwise no problem, you can also calculate it third row first column. How we can calculate third row first column is nothing but 0. This you can see here, we don't have any third row, we have 1 and 2, so here it is 0. Next, if you see in this matrix, we have third row, but we don't have first column. We have second, we have third. We don't have second, we don't have first. We have third row here, we don't have any first column. We have second, we have third, we don't have first. So we have kept it as 0 over here. Clear? I hope it is clear. Why it is 0? Because here you can see third row first column is 0, because in first matrix we don't have any third row, so it is 0. In second matrix we have third row, but we don't have first column, since it is 0. Next we need to see third row second column, that is nothing but minus 4.6 is how it has came. We'll see now. We have third row here, we don't have third row, we have second, first and second, we don't have third, so leave here. Then we'll come here. Here we have third row, we have second column, this is nothing but minus 4.66. so that's the thing what we have substituted here, minus 4.66. Next we have here third row third column, that is nothing but 4.66, which you can see here in this matrix. Third row third column is 4.66, that what we have substituted here, 4.66. This entire matrix we call it as global stiffness matrix that we have seen. Clear? Once we form global stiffness matrix, next step is to form global load vector. Global load vector is nothing but the location of nodes. Like we have two elements, element 1, element 2, and that's what you can see here. Two elements, element 1, element 2. Each element is connected to node 1 and 2. Second element is connected to node 2 and 3. So we have force F1 at node 1, F2 at node 2, and force F3 at node 3. F1, F2, F3. So that's what I have written here, F1, F2, F3. So at F1 the force is 0, since we don't have any force. At F1 is force 0, F3 is force 0. At F2 the force is given 200 kilonewton. You can see in this problem, you will understand here. The application of load is here, that is nothing but 200 kilonewton it is given. Now here if you see, which I have written, F1 is 0, since we don't have the force at the first node. At F2 we have 200 kilonewton, that's what I have written, 200 into 10 to 3. In F3 we don't have load, so I have written 0. Next, this is how we need to form the global load vector. Next we need to go for the global displacement vector, that is nothing but the displacement at node 1 is given by u1, at node u2, at node u3, that's what I have written, u1, u2, u3, u1, u2, u3. Next, once you form this u1, u2, u3, next we need to go for the next step, that is nothing but application of the boundary condition. To apply boundary condition, before applying boundary condition we should form a equilibrium equation, that is nothing but K into Q is equal to F. How it has came here, you can see stiffness is equal to force by unit or displacement. You can write stiffness is equal to load by displacement also. Stiffness can be defined by load by displacement, that I have written F by U. So K into U is equal to F, that's what I have written here, K into U is equal to F. So K is nothing but our global stiffness matrix, and U is the displacements at each node. F is nothing but global load vector, nothing but loads at each nodes, that's what I have written here. We have utilized the boundary condition elimination approach. We are using elimination approach of handling boundary condition. In this, what we need to do, like if you see our problem here, the node 1 and node 3 is fixed, this node and this node is fixed. So the nodes wherever it is fixed, the corresponding rows and columns we need to eliminate. That is nothing but, in the given problem the node 1 is fixed, so we have eliminated corresponding row and column. Similarly, the node 3 is fixed, corresponding rows and columns we need to eliminate. If we eliminate, we left out with only these two. 20 into 20.66 into 10 raised to 4 into u2 into 200 into is equal to 200 into 10 raised to 3. What you have left, 20.66 into 10 raised to 4 into u2 is equal to 200 into 10 raised to 3. That's what I have written here. So if you simplify this, you will get u2 is equal to 0.968 mm. That's what we need to find. At the end, we can write the nodal displacement. U1 is 0 since it is fixed, u3 is 0 since it is fixed, u2 we have found out. So these are nothing but our displacement at node 1, displacement at node 2, and displacement at node 3. So this is how we can solve the problem. Do watch my previous video so that you can understand how to determine stresses, reaction forces. Thank you. If you don't understand anything, you can comment below so that I can answer your questions.